What if the AI systems we use to do research could redesign themselves? Not just fine-tune their weights or tweak prompts, but actually invent entirely new neural network architectures, the kind that might replace the transformer that has dominated the field since 2017. That's the audacious question behind a new piece of work from researchers at FAIR called AIRA, which stands for AI Research Agents, and it offers one of the most concrete early glimpses of what people sometimes call recursive self-improvement. Here's the setup. Almost every large language model you've heard of, from GPT to Llama, is built on the transformer, which alternates two kinds of layers in a regular pattern. Attention layers that let tokens look at each other, and multi-layer perceptron blocks that do feature mixing. But this isn't the only game in town anymore. There's growing interest in state space models like Mamba, which process sequences more like a recurrent network and avoid the quadratic cost of attention. And there's increasing evidence that mixing these primitives in clever, non-uniform ways, what people call hybrid models, can outperform pure transformers. The problem is that the design space explodes combinatorially. If you have 16 layers and 3 possible primitives at each one, you've already got about 43 million possible architectures. Human researchers can't search that by hand, and traditional neural architecture search methods using Bayesian optimization are rigid and don't bring any semantic understanding to the table. So the authors ask, can we just give this job to LLM agents? They propose two complementary frameworks. The first, AIRA-Compose, is what you might call the architect. Agents pick from a fixed menu of building blocks, attention, MLP, and Mamba, and decide how to arrange them into 16-layer stacks. The second, AIRA-Design, is the inventor. Agents have to write actual code from scratch, designing brand new attention mechanisms or training loops. Think of Compose as choosing how to stack different types of Lego bricks, while Design is asking the agent to mold new bricks from raw plastic. Let's go deeper on how Compose works. The agents operate inside a harness called AIRA Dojo, which gives them 4 operators they can use: draft an initial solution, debug a broken one, improve a working one, and analyze what's happening. The search uses a greedy tree exploration, where the agent first drafts 5 candidate architectures, evaluates each one by training small million-parameter versions on proxy datasets, then picks the best and tries to improve it. The crucial difference from old-school neural architecture search is that the agent writes a verbal rationale at each step. You can actually read its design reasoning. Things like, let me try a palindromic structure with attention anchors at the edges, or let me build Mamba islands separated by attention pulses. It's bringing prior knowledge from its training to bear on the search, not just blindly sampling. After the search, the top architectures are aggregated using layer-wise clustering to smooth out noise, then scaled up by either stacking the discovered pattern multiple times or stretching it by widening each block. The scaled-up versions get evaluated at 350 million, 1 billion, and 3 billion parameters. The design framework is more open-ended. Agents are pointed at the long-range ARENA benchmark, which tests how well models handle sequences thousands of tokens long, and they have to write a complete model py file implementing some subquadratic attention mechanism from scratch in JAX and FLAX. They also tackle Autoresearch, a benchmark from Andrej Karpathy where you get a baseline GPT training script and have 5 minutes of GPU time to optimize it for the best validation loss measured in bits per byte. Agents can change anything: architecture, optimizer, learning rate schedule, batch size. One nice twist is the with literature variant, where agents are given 41 research papers and 14 code repositories curated to be relevant, kind of like sending a PhD student into the library before asking them to innovate. Now the results, and they're genuinely striking. On the architecture search side, the agents discovered 14 novel architectures that they group into two families: AIRAformers, which only use attention and MLP, and AIRAhybrids, which also include Mamba. When trained at the 1 billion parameter scale on a fixed token budget, the best AIRAformer beats Llama 3.2 by 2.4 percentage points in average downstream accuracy, and the best AIRAhybrid beats it by 3.8 percentage points. More importantly, when you look at isoflop scaling, meaning how fast the loss drops as you spend more compute, the agent-discovered architectures show steeper scaling curves. AIRAformer C scales 54% faster than Llama 3.2 and 71% faster than the best architecture found by traditional composer-based search. That last comparison is the key one, because it shows the agents aren't just beating hand-designed baselines, they're beating the previous best automated search method too. Interestingly, the discovered architectures converged on attention to MLP ratios of 7:9 or 11:5, which are decidedly not the 1:1 ratio that transformers traditionally use. On the long-range arena task, agents got within 2 to 3 percentage points of human state-of-the-art, with Gemini 3 Pro and Claude Opus 4.6 leading. But here's an important caveat the authors are honest about. The architectures the agents produced were mostly intelligent recombinations of known ideas like performer and longformer, not genuinely new theoretical contributions. The agents are good engineers, but not yet inventors. On Autoresearch, the Opus 4.5 agent augmented with literature achieved a bits-per-byte score of 0.968, actually surpassing the published reference minimum from Karpathy's original benchmark. Reading the improvement trajectories in the paper is fascinating because you can see each agent develop a distinct optimization style. Opus 4.5, with literature, made a single huge leap by swapping cross-entropy loss for focal loss. Opus 4.6 made many smaller incremental tweaks to depth, batch size, and learning rates. There are real limitations worth taking seriously. The Compose framework relies on small-scale proxy evaluations, and small-scale rankings don't always predict what happens at billion-parameter scale. The aggregation and scaling steps are still done by humans, not agents. One-shot agents in the design tasks failed completely. You really need iterative refinement to produce working code. And the greedy scaffold has a quirky failure mode where agents rewrite the entire file at each step, making it hard to attribute which specific change caused an improvement. The with literature augmentation didn't uniformly help either. Some agents got worse when given more context, which suggests integrating prior knowledge into agent reasoning is still an unsolved problem. Now let's walk through some questions you might have after hearing all of this. First, why is searching over arrangements of fixed building blocks even interesting if the agents aren't inventing new building blocks? The point is that the combinatorial space of arrangements is itself enormous, and we have strong evidence that non-uniform interleavings matter a lot for performance. Things like where you place attention versus state space layers, what ratio you use, whether you cluster them or alternate them. Human intuition has barely scratched the surface here, and a one-to-one alternation pattern that transformers use is almost certainly suboptimal for hybrid models. So even constrained search yields real gains. Second, why does the greedy tree search beat Bayesian optimization, the workhorse of traditional neural architecture search? Bayesian optimization is essentially blind. It treats each architecture as a point in some abstract space and tries to fit a smooth surface to predict performance. An LLM agent, by contrast, brings semantic understanding. It can reason that attention layers at the start help establish global token relationships and use that hypothesis to guide its exploration. So instead of crawling through the space, it can leap toward regions that prior knowledge suggests will be good. The paper shows this works in practice. The agents probed just 3% of the 2 primitive space and 0.005% of the 3 primitive space, and still found architectures that beat exhaustively tuned baselines. Third, what's the meaningful difference between engineering synthesis and genuine innovation? And is that a real ceiling or just a current limitation? In the design tasks, the agents recombined known techniques like linear attention with kernel approximations or local windowed attention, rather than inventing entirely new mathematical formulations. The authors are honest that this isn't paradigm-shifting science. Whether this is a fundamental ceiling depends on your view of what LLMs can do. Some would argue that all human innovation is also recombination in disguise, just at a deeper level. The more pragmatic interpretation is that current agents lack the long-horizon reasoning, mathematical depth, and creative leaps that produce genuinely new ideas. But improvements in models, scaffolds, and tool use could narrow that gap. For large-scale recommendation systems, the implications are quite direct. Production ranking and retrieval models are notoriously hand-tuned mixtures of components, embedding tables, attention modules, feature crossing layers, sequence encoders for user history, and the design space for combining them is even worse than what's described in this paper. Because you also have feature engineering and multitask heads in the mix. An AIRA-Compose style agent could systematically explore how to interleave attention over user history with feed-forward feature interactions, or whether to use Mamba-like state space models for very long user sequences where attention's quadratic cost becomes prohibitive at serving time. The latency loss Pareto analysis the authors emphasize is especially relevant. Recommendation systems live and die by serving latency, and finding architectures that scale better in compute means you can either serve more users or push richer models into the candidate ranking pipeline. The Autoresearch style training loop optimization is perhaps even more immediately practical. Recommendation systems are typically trained continuously on freshly logged user interactions, and small improvements in training efficiency compound over months of operation. An agent that can autonomously tune the optimizer, learning rate schedule, and batch composition for a streaming recommendation training pipeline, especially one armed with relevant literature on click-through rate modeling and counterfactual learning, could systematically push the cost-quality frontier in ways that are hard to do with human-driven experimentation alone. The key engineering insight from this paper, that iterative refinement with debugging beats one-shot generation, applies directly. Any production deployment would need a scaffold that lets agents test their changes against held-out evaluation slices and roll back failures safely.